Everybody. I will introduce Helen. Helen will introduce Chris. Chris will introduce everybody, and then we close the session. So, just a very brief word. This symposium today, which is part of a two-day event, is co-hosted by AD Wiley and the Architectural Association, and more specifically, the representative of, let's say, our host today is Helen, who is the executive commissioning editor of AD Wiley Architectural List. Yes. Is that correct? My short-term memory still works. And yeah, just I hope that most of you have received over the last couple of days the program of the day, but I think Chris will quickly talk about that in a second. We will try today to run pretty much to schedule, so it would be really nice if we could make sure that after the lunch break and after the tea break that we can start in time. And without further ado, I'll just pass the word to Helen.
Good morning, everyone. First of all, I just want to thank MTech and the AA for organising this symposium, which is around many of the themes of the new issue of AD, the morphogenetic techniques and technologies in morphogenetic design. I'm delighted and really proud to be launching the issue, and I have to emphasise proud, because in the last few years there's been a great deal of synergy between what I feel that MTech are doing and also what we've been doing on AD. I don't know, probably you're all aware of AD and the various different titles that we produce, but we have the kind of currency of a magazine, of a newsstand journal, and the qualities of a book, which allows a kind of a rigour in thinking. And I think that with MTech and what they're doing in terms of research, there's a very strong fit between AD, which gives a greater space for thought and discussion about research, but at the same time dealing with issues with a topicality that you couldn't deal with in conventional book publishing. The same triumphant, Michael Hensel, Achim, Menges and Mike Weinstock have also been responsible for the emergence issue of AD. Emergence has not only been a bestseller downstairs with Derek in the Triangle Bookshop, but it's now become a seminal issue. We're seeing it being adopted as a set text in the US, which is a kind of really interesting development. We've actually been reprinting the emergence issue at the same time as this new morphogenetic issue. The influence of emergence, I feel, has become palpable. Recently, when I attended the Smart Geometry conference at the British Museum, students from all over the globe, from Korea to the US to Europe, were all at least paying lip service to emergence in terms of jargon. But I think that MTech as a research model has become far more important than the vocabulary, and in my discussions with people all over the world, they've referred to what's being done in this unit at the AA, because it's at the point where architecture in a way has been at a crossroads. How is it going to work with other disciplines? How can it work within universities? They've shown a very tangible model for moving forward in terms of really providing a research education. I think that's what's been very important. Techniques and technologies in morphogenetic design is, however, no emergence too, and I have to make that clear. It's not a mere sequel to emergence. By shifting the focus from emergence to self-organisation and biological research, it simultaneously deepens and widens the potential application for this approach in developing new techniques and technologies. So it starts off with a very in-depth discussions, and if you like, widens up, and you'll see throughout the issue, by the end of the issue, there's far more discussions in terms of with engineers, the smart geometry group, and there's a sense that much of the work is already being assimilated within other disciplines. On editing this issue with Michael and Achim, I was left with a sense of just how infinite this exploration into natural systems is, and how really we're just at the beginning of something. So I'll just leave you with that thought.
I need water. My name is Christopher Hight. There aren't that many familiar faces in the room. I graduated from the AA back in the 90s. So it's nice to be back. And I want to thank Mike, Michael, and Achim for inviting me back. They're fellow travelers. I've certainly enjoyed their presence and visits to where I teach right now, which is the Rice University School of Architecture. And it's lovely to come to their home turf, which is my alma mater. And I also want to thank, I also want to say there are apparently two groups of visitors with us today. Students from HFG Offenbach, and you don't have to raise your hands, and a group from the Berlage with Peter Trumer. Where's Peter? Peter, hi. Anyway, it's great to see some friendly faces, and we'll start the day off. Now, over this day, I guess, the way the next 2 days roughly run is this day is coalesced around the launch of the AD, techniques and technologies in morphogenetic design. And then tomorrow, in a way, I suppose you could think of as a preview or the movie trailer for the book that Achim and Michael are working on that will be published by the AA later on this year. And so it's a nice pairing, grouping that aren't completely repetitious, but also I think in a nice way show what Helen alluded to, which is that this is in a way a very open field that seems to never run out of possibilities and can be calibrated and examined from all sorts, right, different angles. So I'm very happy to be here. All right. So I think as Helen suggested already, the first issue really focused on concepts of emergence and self-organization, whereas this issue foregrounds more tightly, in a way, but also laterally, the theoretical and methodological foundations of a biological paradigm for architectural design, manufacturing, and construction. In other words, processes that are involved around the idea of self-organization. What is self-organization? A little bit of a definition might be in order. They call it, self-organization is the dynamical and adaptive processes through which systems achieve and maintain structure without external control. Roughly, right, they occur through natural evolutionary systems, right, as closed systems. Generally, they try to increase the degree of order, the degree of measurable order, rather than produce entropic decay. The issue is organized roughly around three themes, right? The first is to understand how self-organization promotes functions and properties of systems by increasing the order of a system, right, rather than letting entropic decay take place. How the behavior and performative capacity of this arises, right, from these kinds of neg-entropic processes, and how materials and material systems can be evolved, right, according to such ideas. And then finally, what manufacturing and assembly approaches facilitate this and can manifest these processes. So we aren't just talking about ideas, but we're talking about something that can be put into place, and actually research that can occur through the development of techniques, right? So we don't have this old-fashioned kind of idea that there are ideas and representations of ideas and order, and then what we do and when we make things is we try to represent those. But instead, the research also is embedded in these processes of manufacturing and production and the techniques themselves, which is, I think, is quite interesting today, to understand techniques not as somehow a technical problem, but in fact the most significant theoretical issues that we face today. The issue, and I think today, is roughly organized around, the issue is very clearly organized around three groupings. Today, I think, follows that generally. First, looking at the issue of self-organization explicitly, then examining the questions of behavior, and then finally looking at the issues of material conditioning. Right. So, looking roughly at, in the first sessions, a discussion about self-organization and its relationship to biological paradigms, and also their use in architectural design. How, for example, might the growth of plants and its relationship to external conditions be relevant, right, to the way we understand the design of architecture or other design products. Secondly, behavior, the way self-organizing systems display an ability to respond to stimuli and adapt and change in a dynamic environment. And how, moreover, it's not purely about optimization, but how friction in the system, interferences in the system, actually produce innovation and operations. They can become operational rather than breaking the system, and produce innovation rather than just trying to optimize an already known solution. And then lastly, looking explicitly at the idea of material conditioning, which is the learning process, right, in an organism, where it becomes dependent upon the stimuli of its dynamic environment, and how it gets conditioned, right, according to its environmental stimuli. And in a way, the organism and its environment are locked in a very carefully calibrated dance, right, without which neither one kind of operates. And then looking at how that might be related to digital and computer-aided manufacturing ecologies that are really having a profound impact, right, on what we do. Generally, then, that's the format of the day. Michael Hensel will be speaking first, followed by Jeronimidis and Mike Weinstock. We'll then have a lunch break, promptly resume at 1:45, and Achim Menges will introduce the afternoon sessions. Okay, and then at the end of the day, we will have a discussion among all the presenters today, which I'm sure will be incredibly stimulating. So generally, in this attempt, right, in these two ADs, and especially in this AD, to integrate and understand how this processes of self-organization and emergence relate to theoretical, methodological, and technical practices of architecture. Within that general context, right, I think it's worth maybe pausing at the beginning, and I take this as a sort of license, since Michael asked me to introduce, Michael and Achim asked me to introduce an issue that I didn't edit. And I don't have anything in. I take it as my license, in a way, to go lateral with an introduction as well. And just try to frame in a larger way what might be at stake in arguing for an architecture that self-organizes, that is determined by natural forces, or in any case, a discourse of architecture that seeks to ground itself by references to nature and to the natural sciences, and to derive an architectural order that's supposed to mimic or actually be, in a way, a natural process. And I think it's useful to locate that within the broader kind of debates that happen today in architecture. And so I'd like to maybe invoke the counter-argument, right? The one that says we should not look to nature, we should not look to the sciences as a way of grounding architecture. And that's not because I agree, but I think it does help frame right? The larger things that might be at stake that we may or may not talk about explicitly today. But I think it's always important to project into that larger world of speculation to understand the importance of the kind of work we have today. Rem Koolhaas, in the late 1990s, in one of the famous NE conferences, took issue with Greg Lynn. Greg Lynn at the time was promulgating morphogenetically derived architectural form in a much dumber form, right, than we're going to talk about today. A form largely, when they talk about morphogenesis, when Greg was talking about it, was largely based on animation softwares like Maya, and in a way it wasn't morphogenic at all. But nevertheless, Greg was promulgating morphogenesis and relating all these issues to ideas derived from science, embryology, and so on and so forth, right? The discourses we're all familiar with probably at this point. In one of the discussion sessions, Rem Koolhaas paused and actually was in a way taken aback a bit, but also, of course, typically aggressive. And he said he was really worried about Greg Lynn's promulgation of evolutionary processes, morphogenesis and such. He was arguing instead, right, for a politics of space. He was worried over a scientific approach to architectural form that it forgot the politics of space. It, in a way, sort of naturalized a way of producing architecture. It validated the architecture by references to discourses of truth, and sort of trying to assert that because this is scientific, right, it must be true, and therefore would sort of obscure the politics, right, that any architecture puts into play. And so he argued against that. More recently, Bob Summel, right, has recently publicly declared that, and this is a paraphrase, architecture is not rocket science, or any science for that matter, it is politics. Right? So this is a debate that roughly continues today, promulgated not so much explicitly by Rem anymore, but definitely by Bob Summel. There's an anxiety here about the generalist operations of architecture versus the specialist knowledge that are invoked in these kind of processes. But in general, there's also other anxieties. So we might rephrase the kind of question, right? Why do the sort of architectures that are going to be presented here today and tomorrow provoke such anxieties among these architects? What is the anxiety that's at stake, right? And declaring that architecture isn't a science, but a politics. Now, first, it's important to note that that kind of opposition, right, rests, is architecture a politics, or is it a science of nature? Is it a discourse about truth, or is it a discourse about representation, and so on and so forth? Roughly rests upon a very old dichotomy between the natural and the cultural. Right? One that Bruno Latour argues is the determination of our natural condition. Right? On the one hand, we treat nature as something that is constructed through the cultural practices of science. Right? Science is a cultural practice. It's based on it's something we do. And at least since Kant, right, that world of nature seems to be available only through the representations of the subject. But we also treat it at the same time as something that's transcendent and beyond our control. Right? Meanwhile, we do the same kind of thing in inverse with ideas of politics and society. Right? We treat it as a natural force. Right? It's socially determined. Right? So social forces become a natural force, independent of us, something that we didn't make, even though we know we're all part of society. Right? So we didn't construct the social world, even though we know we did. And this is the kind of paradox, right, that Bruno Latour argues we all sort of labor within in modernity. Now, there's no time to go into that in any greater detail, except to say that architecture itself, right, has continually sort of oscillated between those two poles, right? On the one hand, trying to ground its discourses in relationship to discourses of nature and the sciences, and on the other, to discourses of culture and of politics. And it's done this since the late 18th century, continually. And so, in a way, this debate that happens today can be understood as something that is far deeper, right, and the very core of what constitutes architectural knowledge in modernity, right, or postmodernity, whatever you want to call it, right. Basically, our understanding of what constitutes architectural knowledge is in part calibrated according to that dichotomy and this strange understanding, this strange oscillation between the natural and the cultural, and of course, the technical. But the second thing I think that's worth talking about for a moment is that this dichotomy is increasingly becoming less useful, even theoretically. To understand why, we might, and understand really what might be at stake, we need to recall how architecture as a knowledge in its modern formation also arose with this idea of the modern metropolis, the polis, and the political spacing and production of those subjects. It is in the polis, its public spaces, and its dichotomies of the public and the private that architecture emerged as a professional practice. Recently, a philosopher, Agamben, has argued that every important political question of modernity emerges from a distinction roughly around the public and the private, or, as he argues, a distinction that's calibrated roughly about animal to humanity, right? The human world of the social, the polis, versus the animal environment, given a figure in modernity for humans through the household, the private domain. And in a way, the polis, the public space, was the site where this transformation would take place, right? The transformation from the animal to the human, from the natural to the social. Now, this happened largely through a disciplinary organization of power. Institutions were needed to put into place this kind of production, this transformation of humans into full subjects, right? It required schools, it required hospitals, it required various other institutions. These institutions required architecture. Power required a figuration of itself through institutions. It required a figuration of public space. And the 19th century metropolis. Today, however, we live under a different kind of organization of power and subjects, right? As extensively detailed by thinkers like Foucault, Deleuze, Hart, Negri, Pierre Levy ad nauseum. Today, power does not require, right, institutions. It does not operate on molar ideas of the class, of the race, of gender. It instead calibrates the subject's inner world, right, directly. It operates directly upon bodies, right? This means it doesn't need architecture either, right? It bypasses the scale and intervention of architecture entirely to operate directly on the body. It does not require institutions in the same way. It does not require the figuration of power as form in the sort of urban sense. And in a sense, it doesn't require architecture or even urbanism, right? The sort of scale of urbanism of the street, of the piazza, of the square, of the axis that we know from the 18th century and 19th century metropolis. On the one hand, it operates according to extensive forces of globalization that operate on a transnational scale, right? But in which power is concentrated into a few cities like London and New York. A continuous flow space. On the other hand, genetics, pharmacology, medicine, RFID tagging, smart mobbing, etc., operate at the molecular body of the individual itself, right? The individual body. So the material body has become the privileged site for new kind of informatic manifolds of power and control and indeed liberation, and the incorporation of the organic with inorganic systems. So if in the 19th century, the metropolis was a site where social institutions of disciplinary power were actualized as structures, right, architecture, today power is exercised in scales and in modes that are incommensurable, right, to our objects of architectural knowledge. Agamben has also argued that Heidegger, for example, was the last to, in good faith, be able to argue that the polis, the city, urbanism, was capable of putting forth the politics of what it meant to be human and what it meant to be animal. The discourses about nature, about biological life, have replaced the politics of the social. We have now reached a terminus in that idea. And the most important political, social, and sort of technical developments are being constructed along contours of the body, contours of the organic, that can no longer be determined strictly by human agency or human history. Right? So, the city is no longer the site, right, of politics. So if you believe that architecture is politics, you have a problem, because in a way, political power itself no longer operates through architecture or its sort of larger conglomerations as urbanism. Nevertheless, design, right, it has clearly become a crucial site. All these things that we talk about today, all the sort of operations and technologies that operate directly upon the bios, directly upon the subject, are roughly design problems. In fact, design has trumped every other kind of practice. Right? Bruce Mao is not the only one to argue that in the late 20th century and in the 21st century, design will become the preeminent cultural and technological endeavor. Again, though, what's interesting to note is how our urban and architectural scale is often entirely bypassed, right? At least in its traditional sense. Nevertheless, right, what we are doing was we're designing subjects, we're designing its objects, and we're designing its spaces. And so, in a way, this is what might be at stake in a discourse about morphogenesis in architecture today, right? An attempt to relocate the urbanisms of our becomings, of our subjectivities, of our politics, to relocate those sites no longer in the historical forms of the city, no longer around these dichotomies of the natural, and the cultural, or the politics, and of nature, and no longer held within those historical modes of our discourses, but to begin to operate on the politics of nature itself as a design problem. And in a way, this gets us out, right, of this old dichotomy between an architecture that's political or an architecture that refers to science. And then today, the two have become inseparable. And so in many ways, what's being staked out today is an attempt to push beyond, right, this old kind of modernism and chart out a positive space, right, not a critical space purely, but a new opportunity of possibilities where those old kind of worries and anxieties are really are revealed as pure nostalgia. Okay. The first speaker is Michael Hensel, who I guess is familiar to all of us. I feel very strange introducing Michael in this room. What don't you know about Michael? He likes Asterix, you know, the Asterix and Obelix. Do you know this? He's a huge fan. He's great with children. My son loves him to death. I won't say anything more embarrassing about him. Michael obviously has taught at the AA for, I think, nigh on a decade now. And both in the diploma and as one of the founders of the MTech program. Michael has taught many other places, including, I'm happy to say, with Achim at Rice last year, and produced some amazing work, some of which is cataloged in the AD, in which we'll see today. Michael is also, hold on, I have to find this. I can't remember what it is. Michael is also, this is very impressive, a board member of the Biomimetics Network for Industrial Sustainability. So it's another issue of how this work evokes, relates to sort of broader ecological and therefore political, right, operations, right? That it's sort of false, right, to see any of this as purely a discourse about science or the scientification of architecture, but to understand and produce a new kind of politics of nature. And that's it. Michael.
As is typical with me, I don't know how to use this plastic device here in front of me, so Achim is helping me.
The generation.
No, it's just personal incapacity, which will be probably also the topic of my talk. Nur unten hier mit den Pfeilen. Okay. Okay, let's hope I don't mess up technology here, because otherwise Achim will have to make this way several times. All right. I thought, first of all, to express how happy I am that so many of my friends are here. Not only that I'm happy to see you all, but it also allows me to cast aside a number of the kind of potentially ethical problems of those things that I will put forward today. And I can quite lightheartedly talk about a topic that is probably in some way a difficult one, synthetic life and its implication in architecture. But actually I wanted to sort of greet some of my friends that are in the audience personally, but I thought I opt rather for something else. I would like to take the opportunity to congratulate Juan over there at the end of the lecture hall for having received his Masters of Architecture with distinction in the Emergent Technologies and Design program just 2 days ago. Okay, now that I have gained your sympathies, let me take you on the bonkers ride. About a year and a half ago, when I started talking with Mike and Achim about this current issue of AD, and also some of my other friends, it somehow occurred to me that somehow naturally you want to ask a question: what happens if you don't mind biology as a discipline for easy metaphors or for kind of biomorphism, you know, make something look organic, as it were. But if you would ask the question, what would happen if we would literally apply a biological paradigm? What would we have to think of if we would like to think of architecture as something that is in fact alive? That caused some interesting reactions. For a while I thought, okay, maybe I can't really write this article, but then I thought, what the heck? Because obviously you would expect from friends that they are honest with you, and then once you're over that, you might as well. But also there's one thing that I always do. I always like to pay my debts. About 5 or 6 years ago, that was probably the time that we were last invited to do a lecture here, which is probably nice that you introduced us here, Chris, because we don't get to stand too often here in front of this lectern. About 5 or 6 years ago, I liked to start my talks with a little joke, which was never quite completed, and Mike asked me at that time to once make the effort and try and round the joke up. So since I like to pay my debt to my friends, this is what I will do. And the point is this: I have this little joke with myself that somehow the way in which in the kind of movie world the superhero movies were released sequentially traces in some odd way the 20th century history of architecture. And you will see in a minute or two why this is actually funny in relation to the talk that I will give today. So this was the first one that came out, right? Superman obviously embodies the high modern project, defies gravity without pilotis. Well, at least no visible ones here. Superhuman and invincible if it wasn't for kryptonite, which happens to be green, a favorite theme of my talk. Then, of course, the return of critical regionalism in form of Batman and Gotham City naturally naturally we're no longer heroically flying, we're just kind of gliding in slightly embarrassed ways from ornament to ornament. And then postmodern collage hits the scene with the X-Men. I think nothing much needs to be said here. Perhaps other than one interesting aspect, mutation as the topic of this is a permanent condition. Those people are kind of messed up for good for all the time. They can't switch back and forth. A very interesting realization, as you will see in a second. And then comes the project of the urban surface, right, as introduced by writers like Alex Wall, etc., and somehow the way in which the depth and articulation of the surface and embedded items such as flagpoles, etc., around which you can swing, enable new forms of occupying territory in the city, vague territories such as these kind of glass curtain wall facades. So Spidey, that is where I got to about 5 years ago, and Mike obviously already knew of the movies that would come and challenged me to kind of incorporate that in my kind of joke. So here's the project of the ambient and the haptic. Daredevil, right? I mean, here we have sort of the servo-esque world of architecture, probably a bit of Ocean North, sort of the sound installation, the guy that kind of feels his way around. It's not about so much about form anymore as it is about textures and other sensorial inputs, right? However, here something goes wrong. Obviously, there's always some guys that don't get it right. Here you see Daredevil in Gotham City, and of course that is crap. You know, because this is not about form. So somebody got the wrong picture here, came up with some kind of lapse into collage, which we still witness every now and then in the discipline of architecture, which leaves, of course, the protagonists occasionally quite angry, with others invading their territories and making mean collages out of them. Now, anger is an interesting item because anger is, of course, a response to environmental stimuli. And as you know, this little gentleman here, the Incredible Hulk, reacts quite in intensive ways to a kind of input that you might want to call provocation, and responds by growing about tenfold and turning green. However, here we're talking about a reversible process. Here we're talking about a reversible phenotypical transformation. This is different from X-Men. You can go back to a previous state. This is also slightly different from what you see in nature, with the exception of things such as atavisms, etc. So this is really an interesting condition, and this is the condition that I would like to pick up in the talk today. The Hulk is biochemically charged and emotionally challenged. Welcome to tomorrow's paradigm of architecture, which probably will soon incorporate the scale of biochemistry. Now, if you do a little check over the last 10 years or so of who architects like to talk to, a while ago, we really liked to talk to philosophers. None of us thinks this is something to do today, right? Who talks to philosophers? We like to talk to engineers today. Well, perhaps biologists. Sorry, Chris. Yes, exactly. So, perhaps biologists, but I would say more radical transformation will come in a few years from now, when we begin to talk to biochemists. And what I would like to say here is that what we're learning at present from the disciplines of bionics and biomimetics is a kind of hierarchical structuring of organic matter across many scales of magnitude. However, within the discipline, the best we can do, the best we are doing, is consider perhaps the fiber layout of anisotropic materials. So what happens if we go a step further? Okay. In order to pursue this argument of what happens if we want to literally make architecture alive, the first thing we need to do is establish some criteria. Fortunately, some guys have already done a bit of work for us in that realm, and first and foremost, a Hungarian biologist. Actually, I think he's a chemist. I'm not entirely sure. I think he ventured into biology without having necessarily studied that. A guy by the name of Tibor Ganti, who wrote in the early 70s the Principles of Life. By the way, he's a contemporary of Lindenmayer, and it's quite interesting to see how people from Hungary at that time did some very interesting work. Some were in the field of biology, biochemistry, and perhaps what you might want to call the beginning of certain traits of computational science. So Tibor Ganti generally distinguishes between two sets of life criteria. One he calls real or absolute life criteria, and those are the ones which are necessary for one organism to be in a living state. Among those, he lists inherent unity. A system must be inherently an individual unit. Metabolism. A living system has to perform metabolism, I mean basically energy cycle, etc. Inherent stability. A living system must be inherently stable. This relates to questions of homeostasis, for instance, how your body maintains a somewhat stable temperature within a kind of changing environment. There must be an information carrying subsystem. What that means is probably quite clear. And program control processes in living systems must be regulated and controlled in some sort of way. Then he also states potential life criteria, and those are the ones that he calls necessary for the survival of the living world. And within that, he lists growth and reproduction, the capability of hereditary change and evolution, and also mortality. There are currently many teams in the world that are pursuing synthetic life research. What that entails is the construction of material that can be called alive. Now, this is usually by those research teams is an abbreviated list of life criteria. I will quote Sten Rasmussen from a team at the Los Alamos research establishment. And usually the four employed criteria are containment. I will talk about that in a second, but that has something to do with, for instance, a cell being contained by a membrane. Heredity, metabolism, and evolution. Now, these teams all take different approaches. Some of them try to construct living stuff from a recombination of already living stuff, so organic material or material that exists in living nature. We're recombining this into new kind of creatures, if you like. And then there are some that try to achieve a similar kind of thing from inorganic materials which are currently not part of any living organism. So there are different strategies. It's probably not worth going too deep into it. There are different places in which really groundbreaking research is done. Besides the Los Alamos team, who are constructing what they call the Los Alamos bug at the moment, there are also a number of research networks. There's, for instance, PACE, which deals with programmable cell architectures. That's what they call that. And their headquarters is in Venice, where there's also a bunch of offices and industries located around that topic. But they are teamed up with 14 universities and businesses in the US and in Europe. So this kind of work is taking place, and the discussion of the kind of ethical consequences of this kind of work is usually also entertained by these institutions. But I kind of stay away from that discussion today. Let me go straight into containment. the first criterion. Containment in biology and chemistry is usually given by lipid bilayer membranes. These are membranes composed only of lipid. And this is a prerequisite of cell-based life. Membranes are structures composed, in this case, mostly of lipid and protein that forms the external boundary of cells and of major structures within cells. Since membranes form the boundary between cytoplasm and surrounding environment, they are affected by both environmental stress from the exterior and the pathogenic processes from the interior of the cell. So in some way, this is a very important negotiation device that does not only sets the cell apart from its environment, but it also enables the exchange of that. In terms of industrial applications, there's a lot of research going into what is called intelligent filtration. This is what these membranes do. They let some stuff through, some other not. Some stuff in both directions, some stuff in one direction. Obviously, the making of biological membranes or synthetic biological membranes as of yet is only operating on a micro scale, mostly in the medical discipline and industries, or in microfilters which are used for certain purposes. But you could assume that by the time this research becomes somewhat more broad and that applications are asked for that are of a larger scale, that there might be a way forward. There is a development in what is called smart membranes. And these membranes have to incorporate in some way sensors that will provide a response to the chemicals, etc., whose concentration is to be controlled. A controller that will transduce the response provided by the sensor into a signal that can be processed and transmitted to the third element, an actuator that will drive the controlling mechanism. There are now some kind of smart fabrics that do this kind of thing in some sort of analogical way, but not really quite like biological membranes. There's also some research in what you might want to call tailored porosity materials, where through some way of manufacturing, through some way of chemical, in some case biochemical operations, the porosity of a material is controlled over a gradient. More porous here, less porous there. These things can already be tailor-made. So membrane technology applications include reverse osmosis, ultrafiltration, gaseous diffusion, etc. So there are some developments that are interesting, and we should probably continue to look at them. The second big issue is metabolism. The chemical processes occurring within a living cell or organism that are necessary for the maintenance of life are called metabolism. In metabolism, some substances are broken down to yield energy for vital processes, while other substances necessary for life are synthesized. What you see here is, by the way, an algal bloom turning in some way in the waves green. There's obviously an abundance of nutrition present. The environmental conditions are great, so stuff grows and proliferates. Now, how do you harness that? In which way could you begin to think about harnessing metabolism in some way or another? Well, one of the metabolic processes that is most present on our planet is obviously photosynthesis, the process that converts energy, the energy in sunlight, to chemical forms of energy that can be used in biological systems. This, by the way, is a section through a Christmas rose leaf, which is meant to show you a little bit somehow the distribution of chlorophyll and some other such biological tissue that performs the process of photosynthesis. Now, nearly all living beings depend dependent on oxygen and or the energy production from photosynthesis for their nourishment, make up or is thus making a process of vital importance for all life on Earth. The process has been studied in detail and is used frequently for the development and application of advanced technologies. However, if you begin to research this a little bit, you will probably see that there are a lot of silicon-based photovoltaic cells that claim to perform artificial photosynthesis. Stay away from that, because that's bullshit. It's a different technology, it's a different process that's taking place. However, there are already very interesting types of research going on in the field of how to harness energy or how to use the process of photosynthesis as some way of cleansing or modifying the environment. One such direction is the production of bioreactors, for instance, like this one. This is actually, if I remember correctly, a photo from Imperial College, if I'm not, no, this is actually from a research team in France, but here at the Imperial College in London, there is a world-renowned research team that works in this direction, right? Here, in this case, some of these researchers go into the direction of gaining energy that could be used. Some of them go into the production of hydrogen as a kind of clean fuel to be burned, etc. So there are interesting developments in that kind of direction that will probably soon hit the market on an industrial scale. So it's probably quite interesting to keep these systems in mind as a way of harnessing processes of metabolism, as a way of energy generation for those kind of synthetic life architectures that I'm talking about. The interesting thing is, of course, that the byproducts of photosynthesis could also be, as I've already said once or twice earlier, be the cleansing of an immediate environment. For instance, you get rid through that process of undesirable substances, and you end up with desirable ones such as oxygen, hydrogen, etc. The third aspect is homeostasis. Homeostasis is best described as a property of an open system, especially living organisms, to regulate their internal environment so as to maintain a stable condition, like body temperature, for instance, by means of multiple dynamic equilibrium adjustments controlled by interrelated regulation mechanisms. Now, we know that kind of technology already because that's what most heating systems do with the integration of a thermostat. You measure the temperature somewhere, you adjust the system according to the kind of environmental condition. Again, for this, you need a sensor, a transducer, and an actuator in some way. There are an enormous number of technical devices already on the market. If you just look into sensors, you will be flabbergasted just how many sensor technologies there are. In architecture, we probably use 1% of the available technical devices that are in existence. So anybody interested in that should look into that. However, there's also an entire branch of biomimetics which has turned into a discipline of its own that is called sensorics, where again strategies of nature are studied, where particular kind of sensorial devices which exist in the natural world are translated again into further engineering principles, etc. Homeostasis is probably one of the more easy aspects of synthetic life for us to think about. However, homeostasis relies on a process that's called negative feedback. So it's about the stabilization of a kind of condition. That is not always what we want to do with architecture. Sometimes we want to provide fluctuating or changing conditions. Then we would have to look into positive feedback setups that accelerate change in a sense. There are interesting materials that are developed in relation to that, phase change materials. what I'm showing here is a material that is used for coating fabric fibers called PCM that can absorb and release heat generated by a person wearing this kind of fabric, warming or cooling it as required. If the wearer's body temperature rises after exercise, the PMC absorbs the heat and melts, preventing heat reflecting back onto the body, etc. So there are some interesting material developments in that arena. Then I would like to just add 2 more items onto the list, because in some way I think we have to acknowledge the presence of environment. And what I would like to briefly talk about here is morphogenesis, growth, and differentiation. Developmental biology is the study of the processes by which organisms grow and develop. It comprises the genetic control of cell growth, differentiation, and morphogenesis. This image shows it's basically a snapshot of bone growth, and I won't go too much into this. Now, how do we cope with this issue intellectually and also methodologically? Based on the work of Aristide Lindenmayer, who I mentioned earlier on, and his development of L systems, and basically a kind of algorithm, but this is described at greater length in the AD issue, so I won't go too much into that, has spawned off some interesting work at the University of Calgary, the computer science department, by a long-term co-worker of Lindenmayer and a very interesting researcher in his own right, Prosinkiewicz. And these people have developed some kind of computational growth simulations for plants. What you see here, for instance, is a photo of a palm tree on the left and the digital model of the same on the right. In order to do that, you somehow have to integrate, to some extent, biomechanics into this computational environment. What you want this growing plant, in quotation marks, to do is to negotiate the impact of gravity, the search for positioning leaves, etc., to have optimal exposure to light, and the avoidance of obstacles. So there are some kind of tools which we are presently not really yet using in the field of architectural design that can help us think about this and kind of negotiating different stimuli from a given environment into the design of an architecture. Then finally, I want to quickly touch upon ecologies. I think now I also need a glass of water. Ecology is the branch of science that studies the distribution and abundance of living organisms and the interactions between organisms and their environment. What you see here on that slide is something that I would like to expand on a little bit. Environmental conditions and phenomena of sometimes really quite remarkably large scale. And somehow the features that occur on organisms that are of remarkably small scale, but still able to deal with those pretty severe weather conditions. Ecology can be studied at several levels. There is the population level, where the relationship between individuals of the same species are studied, the ecosystem level, the biosphere level, etc. But what I would like to do now is to offer you a different categorization. But before I go into that, I would like to introduce this relationship that I talked about a second ago to you. A lot of plants have hair. By the way, don't Google hairy plants, because 98% of the web references that come up are of pornographic nature for some reason. Odd. But hairy plants, hair on plants occurs for various different reasons. It's oftentimes poisonous, so it repels the natural enemy of those plants. Those guys don't want to be eaten. Oftentimes, when placed on stems, the hair is there to run off water so that fragile elements don't rot. But when placed on the underside of a leaf, there is a different performance at stake. Oftentimes these plants occur in pretty severe dry or other kinds of environments which are very humid or exposed to very intense airflow conditions. So for instance, along the coast of England, you find a lot of plants growing in the gravel which have to already fight for their territory there, but they also have to cope with pretty severe gale force winds. Now, why do they have to do so? On the underside of leaves, you have small openings that are called stomata, through which the leaf evaporates water or loses it through transpiration. This is actually quite necessary because that produces somehow the condition by which then the plant is able to suck water through its roots up through the stem into the leaf. So there's a kind of cycle here. And this cycle, the degree of evapotranspiration, it's called that because it cannot be quite precisely discerned which amount of water is lost through evaporation, which amount of water is lost through transpiration, somehow needs to be regulated. So if the airflow increases and the stomata are open, the plant would run the risk to dry out. In order to deal with that, the plant grows hair on the underside of the leaf around the stomata in order to modulate the airflow around this region such that the loss of water is regulated to the extent it is affordable to the plant. Now, all of those guys that similarly to me lose hair on their head, don't worry, you won't dry out. You're safe. Now, these kind of hairs is a kind of just as a kind of small indication how even these features might be quite different. Well, actually here in a lemon balm leaf, here in a lavender leaf, and here in an olive tree leaf, you can see that there are already quite extraordinary morphological differences between those features. And that, of course, is a direct response to the environment within which these plants are placed. Now, you would wonder, are there any methods by which we could deploy that in an architectural design? Yes, and here is where, again, the work of Professor Prosinkiewicz's work at the University of Calgary comes in handy. In fact, there are certain methods by which you can map those features onto objects, and you can do that in such a way that it's informed by environmental criteria. However, these things are not scalable. I think everybody in this room already knows that it's the completely nonsensical thing to design 10-meter tall hair because the conditions produced by that are completely different because these conditions are scale dependent, right? So here's, for instance, an attempt, and here I had to borrow a photo from George Jeronimidis' presentation. I hope I'm not kind of taking anything in advance here that he'll be talking about. But what is really quite interesting here is if you look at those, this artifact, you can already see quite a differentiation in terms of thickness and articulation from the top left-hand corner to the bottom right-hand corner. So to some extent, we need to understand the scale dependency of the relation between features and the way in which they modulate the particular kind of microenvironment. And on the other hand, we need to look for manufacturing techniques for their application. Then there is the population ecology, right? Population ecology concerns the dynamic of populations within species and the interaction of these populations with environmental factors. Again, Prosinkiewicz's team has fantastic tools for that. This is, for instance, different distributions of daisies. Very romantic. It's one of my favorite images. Imagine the Incredible Hulk stomping over that. Nothing much will be left. But what you see here is a response to configured maps of the distribution of stuff in an environment. Water, nutrition, exposure to sunlight, etc. So the distribution of daisies here on the left-hand side and the right-hand side is quite different. As you can see on the right-hand side, there's a huge spot without daisies simply because there's no presence of one or several of those conditions required for those guys to be grown in that area. Now this is really quite interesting because you could imagine using these tools distributing some features on architectures in some kind of way. I won't really go too much into the setup of these kind of tools. I just want to make you aware of the presence. There is also community ecology, which concerns the interaction between species within an ecological community and their shared environment. So what you see here is a photo, again, from the English coast on the left-hand side, and on the right-hand side, a simulation over a given amount of time whereby environmental conditions change, and you see that there is a change in the distribution and abundance of different species relative to one another. So I think what we gain from this is some understanding of the size and scale specificity of articulation and behavior, changing notions of component seams and systems, where are things divided, where are they not, and manufacturability, which will be talked about in much greater length later on. We also begin to see that there is one added difficulty. We cannot just concern ourselves somehow simply with the criteria required for something to be called alive. These processes also need to be calibrated and integrated with one another. These underlying processes need to be studied. Interaffection of those things across scales towards higher level integration and functionality. Context specificity of individual and collective behavior and development is important. Changing notions of interdependence and co-evolution. So these are all fields to be looked at. These are kind of interactions between the different things that I've been talking about early on. Then the question is, how do you imagine that? Peter Sloterdijk actually wrote a very interesting essay in which he stated that the very notion of designing an environment in architecture comes from 19th century English hothouses, where for the first time you had to design an environment for alien plant species for them to be able to survive. He said architecture then lost grip of that and the military sector took over. The realization during World War I that you could actually mess up an environment in order to kill people, gas, biological warfare, etc. And only perhaps now architecture is coming back into a kind of position and into an interest where it wants to deal with the modulation of environments again. Along the lines of what I'm talking here, you just have to imagine that you would look at these images and you would no longer be able to distinguish between the architecture and that other green organic stuff here, right? So this would be an interesting challenge. Does it mean we're returning to paradise, to some kind of condition in which the biological and biochemical processes are so ubiquitous that we don't even notice them? They take care of themselves. We live happily and naked around a fantastic environment. I would say no, because remember, this guy is still stomping around, right? I mean, there is a kind of ever more complex condition of interacting with the environment in which conditions may actually be reversible. So we're not talking about a series of sequential developments over time. We have a condition of multilinearity. We have a condition of interaction and modifying in quite a willful manner some things, and a lot of other things will change accordingly, and we won't have so much of a control over that. So it will be really quite an interesting further speculation. And with that, I'll pass the word back to Chris. Thank you.
How come when you look at the Hulk's eye sideways, it looks like a Carl Chu project then?
Which slide?
The Hulk.
Really does. I think you delete this image.
I'm just kidding. Okay. The next speaker is Professor George Jeronimidis, who is the chair of the Center of Biomimetic Engineering at the University of Reading. He also collaborates with the AA's Emergent Technologies and Design program. In addition, he is professor of composite materials engineering and the director of the Center for Biomimetics at the University of Reading. George has a list of accomplishments that would take the rest of the day to read off. Let me just pick out a few. He claims that across all his various endeavors, one of the common themes is how you could supplement and add to man-made designs by exploiting the sort of fibrous structures and operativities that one finds in nature. He has published extensively along those lines in scientific journals and books and many, many conference presentations. He is also on the scientific advisory board for the Max Planck Institute for Colloids and Interfaces in Germany. I want to add a personal note to George's talk. And George came to talk at the AA at one of the many conferences he attends. At Rice last year. And he came to Rice, and I think it was the first time you had been to that part of the world. And George proceeded to give a really lovely lecture, based largely on the fibrous operativity and structural properties of the live oak tree, which Houston is covered with. And in fact, if you remember one of the slides I showed in the general introduction, you will have seen the canopy of live oak trees that blankets Houston, and is basically the replacement for that continuous urban fabric, right, that one is familiar with the 19th century metropolis, right? Houston is a city that is very much alive, right? It's very much a capitalist monopoly game. There's no planning, there's no zoning. It's completely driven by private interest rather than any political public operations. And yet what coheres the city are these trees, which produce this kind of amazing dappled light. It modulates the heat. It contours the wind flow. It provides shading. And in fact, it also produces this kind of strange condition where one is never quite exterior, right? You're always in this strange interior-exterior hybrid condition, right, underneath the canopy of trees. And it links together all the very disparate collage elements of Houston. And George came and presented about how the molecular organization, right, of the wood in these trees produced these kinds of larger effects in many ways. And so this to me was a brilliant example of how very specific kind of research that one might think is structural or technical in nature in terms of architecture actually interfaces directly and kind of magically with larger kind of social, atmospheric, and environmental conditions that we face every day as architects in the modern sort of post-metropolis. So George, it's lovely to hear you again, and welcome.
Thank you, Chris. Thank you very much. Well, as Achim here helps to get things underway, I want to thank Chris actually for the opportunity he gave me to visit Houston and the School of Architecture at Rice. It was a very interesting symposium on motivation in architecture, and again, it's the same kind of argument. In other words, what are the levels of knowledge, what are the sources of knowledge that one feels one needs to bring into architecture for future developments. I'm also going to thank again Mike and Achim for the opportunity to say something about one of my pet subjects. I apologize to some of you because having given lectures here, some of the things would be not quite repetitions, but you may have seen bits of it before. The title that I chose was to do with the geometry, materials, modeling, and simulation, and they're not going to be dealt in that particular order. In fact, it's going to be a mixture of all these things together. I'm going to leave the geometry details off later on because there's a whole session this afternoon which is going to cover some of these aspects. What I do professionally is teach and research in these kind of areas which have got one common feature. On the one hand, I'm interested in structures, engineering structures, civil engineering structures, whatever.
and on the other hand, in biology, we see a lot of structures. The one thing that attracted me to look at these two things together was the fact that in both these kind of areas, I can see enormous opportunity for fiber structures, as Chris mentioned a moment ago. In fact, if you take away fibers from biology, you've got very little left. In fact, there is no biology virtually without fibers. And going back to the points that Michael made about synthetic materials, okay, the other message, which I think is important to realize, is that there is really nothing very special about the materials of biology. They are really pretty mundane things, okay? Chemically, nothing special. Mechanically, nothing special. Biochemically, nothing special either. It is really the way in which they are integrated, put together, organized, and then providing the higher level of structure. That is really the challenge. The materials themselves are almost irrelevant, okay? It's what you do with them and how you put them together which is really the challenge, both for engineering or architecture. So if I think about architecture myself, not being an architect, but my background is mechanical engineering and my biology comes from interactions with colleagues on the research side. When I started looking at or interacting with people in architecture, I mean, of course, architecture is about creating shapes and creating volumes, open spaces, whatever you like. And in many ways, we can go down one level and redefine these things as surfaces or planes or curves, or call them shells or plates, lines, cables, whatever you like. And my interest really in all that is, okay, well, what are the best solutions to convert geometry into reality? Geometry really has got a very, very important part to play. And in fact, one of also the interesting things about biological systems as opposed to man-made systems is the fact that biology exploits shape and geometry to a much, much greater extent than we are either capable or willing to do ourselves. Going back to one of the reasons why you're going to find this thread of fibers going around is the fact that if you look at some of the topic areas of the symposium, which is emergence, which is self-organization, etc., etc. This is a beautiful example on the right, is the structure of the head of your femur, where the three chemicals involved are one protein called collagen, which is a fiber system, which makes up also parts of your skin, your tendons, etc., etc. There is calcium hydroxyapatite, which is essentially a mineral, and then there is water. So those are the three basic ingredients, and you can see that none of them is particularly sophisticated or particularly special. What is special is the way these things can integrate together. And in bone, we have a beautiful example, indeed, of what a dynamic system is, because bone is one of the few materials, or few structures, if you like, which remodels itself continuously. So there is information which is coming in from the outside world, processed by appropriate cells and then translated into reorganization of material all the time. That's the reason why if you don't walk, the bone doesn't know what kind of loads it's supposed to carry, and therefore it goes all over the place. It cannot make a decision, essentially. And that brings in another point that Michael mentioned, is about the question of morphogenetic design or self-organization being something which is not subjected, well, is not controlled by external influences. It's a self-internal control. That is true. On the other hand, if you do not have the interaction with the outside environment, you don't have the information that you require. So internally, it is a question of self-organization, but the outside world still has got to be present, because that creates the local conditions in time or space. And we can see that again in biology. We've got two time scales for adaptation and self-organization. We have a time scale which is measured in evolutionary terms, okay? This is the genetic information which is accumulating. But also we've got the adaptation at on a very local level, either in space or in time, which are really changing conditions. And the examples of that is go into any kind of situation where you've got allegedly plants of the same kind, and you will see that there is a great variety of shape and form, because every one of them is working in a very small subset of environments. And the same applies to bone. And okay, in mechanical engineering terms, this is a beautiful example of mechanical optimization, but in a dynamic sense, not in a static sense. And we can map out the stress field inside, looking just at how the material has been reorganized itself internally. There is no question that if you do not have fiber systems, that kind of optimization is impossible to achieve, because materials that we normally are using in engineering or in construction are isotropic, i.e. they have the same properties in all directions, and therefore by definition, if you go to optimize with respect to a given set of loads, you cannot do it. Because if you go to the same properties in all directions, unless the loads are coming from all directions as well, you're always going to have some directions which are over-designed compared to others. But fibers allow you to get rid of all these constraints, because in theory, this is the sort of dream of everybody interested in designing with composite structures, is to organize the fiber structure so that it is really a map of the stress mechanical forces coming from outside or inside which are on the system. So if you take morphogenetic design as the topic, okay, we've got a number of aspects which are the attributes, if you like, of a morphogenetic design. We've got the emergence, the adaptation, and the self-organization. And again, other speakers will cover that in greater detail. My interest is really to say, okay, well, what do we want out of all that? Well, what we want is some higher level of functionality, presumably compared to what we already have. Okay, we are trying to get better systems, whatever better means. Okay, and the question is, what are the best technologies, okay, which we can put into practice in order to achieve this kind of functionalities? So we've got materials we can choose from, we've got structures we can organize, more importantly perhaps we've got hierarchies, okay, and this is really where a lot of the interesting paradigms from biology come from. In biology, as you've seen from some of the pictures that Michael has shown, are not monolithic objects. What you see are incredibly clever and sophisticated levels of structure, starting from the molecular level up to the whole organism. And I don't think we understand enough of what is the potential of hierarchies in terms of emergence, adaptation, and self-organization. So again, the other organism which does to some extent adapt and integrate a number of functions are trees. Okay, plants in general, but trees more specifically because they've got bigger problems than other plants. First of all, they are permanent structures. A lot of other plants may die off and grow again every year, but trees cannot do that. I mean, once they're there, they're there. They have to grow in size because of what they're trying to do to intercept sunlight, and that brings additional mechanical problems, of course. And this is just to run you through some of the techniques which biology uses in terms of materials, hierarchies, and processes in order to achieve this kind of self-organization. We see a shape which is indeed the result of a self-organization process internally. Information is passed out, is communication between cells via, for example, chemical means through the membrane, the bilipid layer, and however, again, I stress the fact that this thing is the shape it is because it is also capable of sensing changes in the environment in which it's growing. If you think about that thing, it's doing a number of things. Is obviously is a beam, okay, or several beams actually, so it's a mechanical function. Hydraulic function, I'll come back to that in a moment, the energy management, the shape optimization, the temperature control, and you can go down and find a few more things. The hydraulic one is really quite a fascinating system if you think that big trees, the really big trees, 100 meters or more, are actually pumping massive amount of water from the root up to the atmosphere over 100 meters, and there isn't a single mechanical pump in sight. Okay, everything is done by playing around with the chemical level, the materials level, the hierarchical level, and of course the control of the transpiration through the stomata cells at the top. So they are good archetypes because they provide ideas how to tackle some of the problems we have. okay, can we replicate some of these things? This is really what biomimetics is about. So again, it's materials, structures, it's hierarchies. And what I'm going to do now is to go down into the tree, so to speak, in bits and pieces. I mean, one of the first things that you see if you cut a branch, for example, is that it's not generally circular. Although it may appear circular from the outside, it's very often actually very eccentric. That eccentricity is just an adaptation. The branch needs to stay at a particular orientation in space, okay, and it's got two mechanisms for achieving that. On the one hand, it can grow more in one direction or another and become a more elliptical section. We know that from basic beam theory in engineering. But the other thing that it does, if I can find the pointer, okay, so this is the biological center, if you like. This is where the tree started growing outwards, radially. But what am I doing here now? What it does is also to increase growth in that direction here. And that's not the only thing that it does. It does increase the growth, but in addition to that, is also providing a modification of the basic material. So there is an adaptation, not just in the shape of the branch, but there is an adaptation internally in terms of the microstructure of the material which is used. So, stop that. Ah, yes, that would be useful. Is highlighted something there. Okay, that's fine. It's all under control, yes.
Just a second.
Yeah.
I think it's better to use.
Yeah. Right. Okay. So this is just one level down from the whole organism that we've seen before. Okay, and all trees do that, and you can see that actually in very extreme conditions. For example, in the buttresses that you see in some South American trees, is nothing but again the same kind of process pushed to the limit. If we go one further level down, okay, at the level of the cells, these are the cells which, contrary to the ones that are just relying on a lipid membrane, I mean, this is true for animals, okay, it's not true for plants. In animals, you need additional materials and additional structures to actually be able to carry loads. If you don't have bones, okay, your cells are not sufficiently strong or sufficiently stiff to let you walk, okay? In fact, the only animals which can live without a skeleton are in water because you don't have gravity. The moment you go on land, you need some stiffness, okay? In animals, stiffness is coming from skeletons, either exoskeletons in insects or internal skeletons in mammals. In plants, the skeleton is part of the cell. Okay, so as well as the lipid membrane that Michael mentioned, there is an additional layer of fibrous material, and this is absolutely crucial because it is through the manipulation of this structure that the plant is capable of adapting, growing, and reacting to the environment. So if this is a typical structure of a wood cell, it's an elongated tube, okay, it's about 1 to 5 millimeter long, it's about 30 micron in diameter, so it's a small object, but not infinitesimal a small object. And what is important is really the fact that it's made of several layers. In each layer you've got cellulose fibers, and the cellulose fibers, as you can see, have got different orientations in different layers. That's one important difference between the layers, and the fiber orientation can be changed in the layers. The thickness of each layer can be changed, and these changes are really the result of receiving information from the outside and restructuring on the inside. So it's a kind of level of self-organization, again, dependent on sensing. And these are just micrographs of the same thing. This is showing just the interface between the innermost layer, which is the one where the fibers are very highly parallel to each other, more or less along the axis of the cell, and this is the outer layer where the fibers are more going in that direction. You can see that depending on local conditions or different species, you can have additional stiffening elements inside. You can have integrated channels which are necessary for moving fluid around, and you can see here two of those in more elliptical shape. And of course, everything around here is made out of fibers which are patterned out in particular situations. So that's where the games are played. And these are examples of the specialized wood which is fabricated by the trees when they have to respond to changes in gravitational inputs, or simply the fact that they are growing initially oblique and they want to go straight. So nothing has changed in terms of the chemistry. We are still talking about the three basic chemicals: water again, cellulose fibers, and some glue to stick them together. But here you got different shapes which are coming up. The thickness has changed. You get this spiral thickening inside. Okay, this is for compression wood, and this is for tension wood. You get an additional, complete additional internal layer of fibers which are very highly oriented in the fiber direction, in the axial direction of the cells. So again, these are just examples of self-organization, and you can start from the incredible, amazing regularity of the microfibrils, okay, and then the patterning out, and this is really the question of orientation, fiber-fiber interactions, and layering. And don't forget also that one of the important things that this kind of arrangement of materials can give you is not only this possibility of matching different requirements in different directions, but is also capable of creating differences at different levels of structure, and those differences are in fact part of the driving mechanisms for the adaptation and self-organization at the global level. So you can do things at the local level, sometimes the micro level, and then having the knock-on effect of this design telescoping all the way up to the main structure. So I'll go through those a bit more quickly. We've seen a few pictures of that. Okay, so we've got cellulose and we've got glues sticking them together. Really and truly nothing different from what we do when we fabricate with our own composites. One of the things that plants do, of course, is they have to organize these fibers, and the organism or the elements which are doing this job are in fact on the lipid, bilipid layer, the membrane, the biological active membrane. Those are enzyme complexes, okay? They are called rosettes, and each one of those things is one block of 6 enzymes, and these are really the equivalent of spinning machines, okay? The cellulose is manufactured inside the cell, here, below. The blocks which make up the fiber are put in here in this enzyme. This enzyme assembles, glues or stitches the monomers one after the other, and out comes the fiber, okay? And you've got lots and lots of those, and if you look at this picture here, you can see that these things here are capable of moving around, and as they move around, they leave behind, essentially, the fiber. So the patterning out and the changing of orientation of the fibers in the cell wall is due to the movement of these manufacturing entities. Okay? Now, nobody quite knows where these things are getting the information from. Okay? We know that the tree responds in a particular way, but the regulation and the information processing is still a long way from being understood. But this is how your fibers are patterned out. And this is one of the macroscopic results of this exercise, okay? This is a tree which actually has been, the leader was here, the leader has been cut, and when that happens, the tree again tries to go back up, and the only way to do that is to have one of the laterals to take over the function of the leader, and he's got to do that in a very short time, because otherwise it's going to be sort of at a disadvantage with respect to competitors. And you can see that the lateral, which was growing originally in that direction, suddenly has got the information that the leader has gone missing, okay, and that he's got to take over, and he's got to therefore change his orientation in space very, very rapidly. And he does that precisely by getting this information, processing the information, and then lay down the right material to take advantage of the differences in fiber orientation that I mentioned before. And this is, I was talking about modeling, okay, can we model that? Well, this is something we did a few years ago, same kind of process with deciduous tree this time, a poplar. Okay, it was grown originally at an angle, and we monitored the change of shape of the tree as it grew over about 6 months, and it started like that and eventually reached that position. Now we can understand that the way to do that is to create internal stresses, and these internal stresses are the result of this differentiation of the fiber structure at the level of cell walls. The normal wood looks like that. The special wood, which occurs only when you have to deal with this problem, looks like that here. The difference is the fact that when, during the process of biological maturation, if you like, what happens is that this wood here shrinks more than this wood here. And so if you got them on opposite side of the trunk, so you imagine the normal wood is here, the tension wood is here, okay, and this is across the trunk. This one is shrinking, but this one is shrinking more, okay, and the result of that actually is curvature, not in that direction. It should be the other way around, okay. But it is this internal self-stressing of the system which actually creates the change of shape. But again, the trigger for that is the change of water content, but the mechanism which is necessary is the differential organization of fiber structure at this level. And if we understand the stress generation mechanism, if we understand the regulation mechanism in time and space, how much material is needed, where is the material which is needed going to be deposited, in what kind of rate is it going to be deposited. If we can put all these things together, then we can start modeling. This is a completely 100% computer model of the reorientation of a tree of that kind. We can go one step beyond that, because we can use some of the things that trees do, and this is not just for trees, okay, other biological structures do the same, and is really to use this biological information to create algorithms which will allow us to optimize, and in terms of shape as well as in terms of internal structure, to optimize in an adaptive way. And this is some work which was done by Klaus Matek in Germany, in Karlsruhe, okay, where he's looked at trees and fork of trees, I mean, notoriously weak points in a structural engineering context, okay, to look at what is the shape which the trees decide to go to. Okay, remember that that shape is obtained as a result of two phenomena. One is growth, but growth which is not passive, growth which is interacting with the environment all the time. And the second one is the internal possibility of reorganizing material and fibers in particular directions. And what he has done is essentially, first of all, confirmed that the shape that the trees goes to is indeed the one which creates the minimum overstressing of the structure, which is what you see here. The red things are bad things, okay? But more importantly is the fact that you can use this information and translate it into an algorithm. So now you can optimize a structure, at least mechanically optimize a structure, by just looking at that kind of approach. So since I've said that fiber architectures are really the key to all that, then let me just give you some examples now of what we technologically can do, although I have to step back to some biological system from time to time. Okay, well, this is the spiders which is making silk, as we know, a fascinating material in its own right, a lot of interesting things. But we really do have almost the same kind of technology available. This is a braiding machine. Okay, the braiding machine is essentially organizing a tubular type structure by a technique which is really very, very simple. Okay, it's a fascinating thing to see happening, but in fact the geometrical topological effects are very simple to understand. Okay, but the question is what we can do with these things. Okay, well, let me go back for a moment that when you're using composite materials where the fibers are the real load-bearing elements, you really have, first of all, an enormous flexibility in design, way, way beyond what you can achieve with the more conventional materials, because you can organize these fibers in different orientations, and because you can organize different layers with different fibers in different orientations. And this is what we see in a lot of biological systems, okay, whether they are sort of animals here, you can see layers of cell walls with fibers going in different directions for specific purposes. Some of them to do with locomotion, some of them have got to do with structural stability, some of them have got to do with actuation. Here you find the same thing, and organizations of fibers in this kind, you find them all over the place, whether it is plant cell walls, exoskeleton of insects, layers of skin. All of them are essentially, again, playing games with this kind of entities. One of the interesting things which is also happening in biology is the fact that fibers, from a mechanical point of view, are elements which are essentially tensile structures. I mean, they are at their optimum when they are carrying tension. Fibers are not very good at carrying compression. Biology has discovered that problem a long time ago, and the way it bypasses the problem, given the fact that it carries on using fibers as the building blocks, is to make sure that in all these organisms, the fibers are always working in tension as much as possible. And you can achieve that by pre-stressing, and that pre-stressing can come either from the fiber organization or can come from fluid pressure created as part of the functionality of the whole organism. Sharks are pressurized systems, okay, and a lot of squid-like objects are pressurized systems. They need the internal pressure to stabilize the fiber pattern, which allows them to perform the way in which they perform. Sharks do not have a skeleton, okay, in the normal way. It's got a kind of gel inside, and it's the pressurization of the gel which interacts with the fiber pattern to give the stability, if you like, to the system. And you can find these cross-helical arrangements in tunicates, squids, and things of this kind. The pressure is generated by muscles in the case of animals, but we find the same thing in plants, where the pressure is generated by chemical means. Sorry, this one is. And then we have also the interesting point of a transition which occurs in plants in particular between the early stages of development, where the fibers are pre-stressed in tension by the internal pressure created by the chemical system, okay, and this allows also the plant to grow, okay, by not only multiplication of cells, but also elongation of cells. That's part of the process of growth. And in this process, if you take something like a bamboo, okay, these are the early stages of growth of bamboo, which is extruded essentially from the ground. Okay, everything is happening here. There's nothing happening up there, okay, or comparatively little. Is the fact that as the thing is growing, is also integrating during that process. And again, I think this is a good example of self-organization. Okay, these septa here, which are necessary to improve the stability of the system against buckling when it is bent by wind loads. And what is fascinating to look at is really the detail of the fiber organization in the area of the joints. Because in mechanical, civil engineering, architecture, whatever not, okay, we design shapes on a computer. We've got overlapping and crossing bits of elements, okay, which look very simple. But in fact, 90% of the nightmare of actually putting that thing into perspective in terms of realization is really the astronomical expense of time, effort, and ingenuity which goes into making the joints. Biology has got the same problem, but the way biology solves this problem is quite different from ours, because in biology, joints essentially do not exist. Do not exist because the fibers can go around, and there is a geometrical joint, but there isn't a mechanical joint to speak of. And we see that in lots of plants as well. And again, the hydrostatic pressure helps to keep the fibers in tension. Okay, it's also important to realize that pressures up to 20-25 bar are capable inside plant cells. Okay, this is 10 times the pressure in the tires of your car. Okay, so these things are really very highly stressed. That is what allows the fibers to provide the functionality that they do, is because you've got this very high level of stressing coming from the internal pressurization. And that pressurization, of course, has got also an advantage in terms of stability, and this is again how internal pressure can help. But of course, you can see now here, this is forget about this. This one here is just a hollow tube, okay, a composite hollow tube, actually made of glass fibers, pressurized internally and then bent. And what we wanted to see was how the critical point of bending changed with internal pressurization. And you can see that there is a significant advantage in terms of the load carrying capacity if you pressurize internally the system. Now, the one thing which is important is the fact that the fibers we can make, like the fibers in biology, can take deformations which are typically 5 to 10 times higher than the one that the best steel in the world can take. And the result of that is that we can afford much higher level of pressurization in this system than we will ever be able to get into a conventional material. These are some of the strange things which can happen in composite structures when you start coupling anisotropic effects due to the fiber orientation with heterogeneity effects due to the layering of the structure. But rather than spend time on this one, I'll just go through some examples. Okay, one of the most interesting things that you can do is that with composites, this is now our main-made composites, okay? But we're using the same tricks, if you like, or part of the same tricks as biology. What we can do with composites is to design certain characteristics. This one is fascinating because with layers of material where nothing has got a coefficient of zero expansion, in other words, the material will have a coefficient of expansion in that direction, which will be different from the coefficient of thermal expansion in that direction, of course, because that's the anisotropy of the fibers. If we now pile up or layer this thing, we can look at what is the global thermal expansion coefficient, not the one belonging to one layer or one direction, but what is the combination of the thermal expansion coefficients when you start layering these things. And what you can get is fascinating because you can get material here in that position and in that position which actually has got a zero coefficient of thermal expansion on a global scale, although internally every single element separately will expand or contract with temperature. There are applications where having zero coefficient of thermal expansions are incredibly important. And again, especially in joints, one of the biggest problems for joining different materials is that when the temperature changes, they want to expand or contract by different amounts. And therefore, they create internal stresses which are not desirable. And here we can create structures with playing around with fibers, and space applications are particularly sensitive to these things. If you've got a part of a satellite which has got to go from minus 300 degrees centigrade to plus 200 degrees centigrade as it turns around the Earth, it does make an awful lot of sense if you can have a zero expansion due to thermal problems. We can use the same trick to make adaptive shape in turbine blades. This is a project we had a few years ago where we can construct the structure of the blade using fibers and layering in such a way that as the blade goes around, the centrifugal load on the blade is actually changing the shape of the blade, really twisting the blade, and that twist then is used to slow the blade down. So we can create a desirable aerodynamic effect purely because of the change of shape. And that kind of technique is impossible to do without fibers. Only fibers can give you this kind of trick. We can do other things like embedding sensors we talked about and that we're mentioning. Sensing is a very important thing, and all the biological sensors, okay, are really part of the structure that we see. They are part of the material, they are part of the hierarchy. We don't see things in biology which we call sensors. The sensors are essentially fully integrated with the material, with the structure, with the hierarchy. And we are moving in that direction. This is an optical fiber sensor. As you can see, those are carbon fibers. The diameter is still too big for comfort, but as technology advances, okay, one hopes to reduce the size of that to be a bit closer to the size of the load-bearing fibers. But it is important because it is something, again, which we can do with composites. We can't do it with metals. And we can do it with composites because fiber optics is just fibers, and in the same way as we handle the structural fibers, we can handle the optical fibers. Back to fabrication, okay, a reminder of what happens in the cell wall. This is how the spider spins his silk, okay? He's got a bag of chemistry under that, the spinnerets, and every one of those is essentially providing a filament of the silk, okay? And it is really no different from one of the braiding machines. If you imagine a system like that where these individual organs can be moved around in concerted fashion, you create a braided structure. And this is what a braiding machine looks like. Okay, every one of the spools is carrying fibers, and then there is a kind of magic dance of this thing, and you can control the size of your tube, you can control the fiber orientation of the braid, you can control everything. Structurally speaking, this is an amazing kind of technology, because here you can create this shape starting from what is essentially a tubular structure. So you don't have joints, you have continuity of fibers because the fibers are running continuously through. And you can modify locally the geometry, okay, and create whatever attributes you want in your system. These are filament winding examples where we can create junctions between orthogonal tubes, which is a notorious difficult problem in whatever material you want to play around with. But here again, we have essentially no discontinuities, or certainly far smaller discontinuities you might have in a conventional fabrication technique. And we can make these things as big as you like. The rocket case of the big launchers are enormous pressurized vessels like that. Really, this thing is just a gigantic wood cell, okay, or plant cell, nothing more, nothing less. You pressurize the liquid inside and you create a structure outside to contain the pressure. One other technique which is fascinating, because again, it provides a shape, a design of shape without having joints or connections, is to use what is called the resin transfer molding process, which is a bit like our bone, actually, where the first thing which is laid down is the pattern of fibers, very flexible. This is what happens when you are very, very small, just after birth. You don't have lignification, you don't have mineralization of your bones. Your system is still very flexible. The collagen fibers are there, but the mineral is not there. And so you create, first of all, the shape and the architecture with the fibers. You can modify that shape as we've seen before. And once you are satisfied that that shape is what you want, then you can rigidify the whole system by either injecting resin or spraying resin. The techniques are several. You can make very complicated joints, again, which are far, far more efficient than with standard materials, again, because the fibers are running all the way through the system. You don't have ends of fibers which create additional stresses on the local level. And if you want to incorporate additional functionality, okay, this is just a braid, and for some of you may have seen the film I, Robot. Okay, all the robots that you've seen have got what I call pneumatic muscles. Pneumatic muscles are nothing but braided structure like this one with a balloon inside, and you pressurize them with air. And as you do that, depending on the orientation of your fibers to begin with, that thing can contract. In biology, that happens too on a smaller scale in plant cells, for example, but the driver is not compressed air. The driver is chemical pressure or chemically generated pressure, and this chemical generated pressure can be used also with what are called active polymer gels. So if you take one of these things, active polymer gel, you put them inside the braid and expose them to water, okay, the gel will want to absorb vast amounts of water, will try to increase in volume. The braid will constrain that increase in volume of the gel to be translated into a contraction of the whole system. So you got again a kind of emergent behavior here, because you've got something which by itself will swell in all directions equally. If you add the fiber pattern, and depending on what fiber pattern you add, then you can create something different. And to me, this is really what fibers can give you. And we can model all these things. We can play around computational games as well as physical games. So this is the braided system, okay? If we put fibers which are oriented in the axial direction of the braid in this side, for example, as the gel expands, it will increase in volume, but it will also be forced to bend. If we put patterns of helices of fibers here, which are not the same in the two left-handed and right-handed helices, either because they are different materials or because they are different density of fibers or because of different cross-sectional area, we can force this thing actually to twist on itself as it expands. So you can get contraction and twist or expansion. So in conclusion to all that, okay, again, to me, the biomimetics is really something to provide inspiration in the first instance, and perhaps looking at existing solutions which can be translated. No matter how you look at it, if you want to think in terms of the implication on morphogenetic strategies, you need to take into account a number of things. First of all, the differences which are created at the local level, differences which, as we said, biology is capable of creating because it can play this enormous range of games with fiber patterns. You need the hierarchies because that's the mechanism by which you can translate these differences at the local level into some functionality at the global level. These are essential for coupling between local and global events. Then the fibrous architectures, because they provide an almost unlimited design space, as indeed biology is showing. And at the end of the day, okay, I reiterate what I said, not only the chemistry in terms of the material chemistry, the substances, is actually very simple. There is nothing special or nothing magic about it, but also the mechanisms which provide biology with indeed all the things that Michael has mentioned and I've touched upon as well, are actually coming from very, very simple physical principles. The physical principles are easy. The implementation of the physical principle, in other words, the translation of the physical principle into an emergent behavior, into self-organization, optimization, whatever, that is really quite difficult to understand. This is what is, to me, the most important area from the biomimetics point of view, is really to understand how that process of going from a basic physics to a kind of functionality actually arises. And this is just an example for something which is very difficult actually to replicate in is really, again, a form of adaptation of the system. I mean, it's a tree growing against an obstacle, okay, and instead of pushing the obstacle away or trying to fight it, is simply incorporating whatever is got within his own structure. So it's just growing over it, essentially. That means, again, that he's got to have sensors here which are capable of sensing contact and translate that information into the thing which is going to produce the growth. Growth is one of the things that we cannot do very easily. And actually, this is where I think the geometrical computational systems are really going to be one of the most important tools, because it is one way in which we can at least conceptually see what the effect of growth will be, okay, if we could have it, okay, is really to play sort of on the modeling side with these things here. Okay, thank you very much.
Right. Our last speaker this morning is Mike Weinstock. Again, it's one of these tricky things.